This is lesson 2-3 for secondary 2 math, and today we're going to talk about the similar triangle proportionality, specifically a couple of theorems that work with similar triangles. The first thing that you see on your notes is the triangle proportionality theorem, and it says that if a line is parallel to one side of a triangle and intersects the other two sides of the triangle, then the line divides these two sides proportionally. Before we prove that theorem, let's actually look and see how it works. So let's move on down to the examples below and look and see what this is. So we've got this larger triangle here, this one, and we have a line that's dividing these two sides. So it's dividing this side and it's dividing this side. And so what the theorem says, it says if these two lines are parallel, which they are because we can tell by the markings, then it splits these pieces proportionally. So if I was to write a proportion, I could write 3 to x plus 4 is equal to 2 over 6. So I could write a proportion like that. So as we know from proportions, we can write proportions in a few different ways. And I would prefer my variables to be on top, so I'm going to write 6 over 2 is equal to x plus 4 over 3. And then I can solve that proportion, solving for x. So go ahead and pause the video and solve that one for x. We can use cross products, so we can say 6 times 3 is 18, and 2 times x plus 4. So 18 is equal to 2x plus 8. Okay, to solve that, you're going to subtract 8 from both sides, and x is equal to 5. And so because of the triangle proportionality theorem, we know that this is 5, so this side is 9 to 3, 6 to 2, and that proportion is the same. So let's go to the next example. So find the length of EC. So that's this piece right here that's x. So I know first off that this line is parallel to this line. So because of that, I can use my triangle proportionality theorem. So again, because I want the x to be on top, I'm going to say x over, and then I don't know what this piece is right there, so one way that I can do this is I can say x compared to the great big piece, so 21, is equal to what's going to compare on the other side is 3, not to 4, but to the great big piece. And so make sure that when you do your proportions that you're setting up equal corresponding pieces when you set up your proportion. So we can solve this again by using cross products. So I'm going to have 7x is equal to 63, and so x is equal to 9. So this is 9, and so then that would make this side equal to 12. So 9 to 12 reduces to 3 to 4, and so our proportion works. Okay, and then the third example, before we prove the theorem, if AC is equal to 60, so this whole thing is equal to 60, and EC is equal to 36, then question is are those two lines parallel? And so we're trying to see if everything's proportional, because if it is, then the lines are parallel. So let's set up a proportion. We can say 18 to 60 equals 24 to 36. If that's true, then the lines are parallel. If it's not true, then the lines are not parallel. So you can check your cross products and decide if they're parallel or not. Okay, so when I set up my cross products, 18 times 36 is 648, but 60 times 24 is 1,440. So they're obviously not the same, which means that these are not parallel. Okay, so let's go back up to the top and let's look at proving the triangle proportionality theorem. I'll tell you right now you're going to need to write small, okay, but let's start out with a picture of what we're trying to do. So I'm going to start with a picture of a triangle, and I'm on purpose making it look like it's scaling, and then I'm going to draw a line that is intersecting the two sides. And the part of the theorem, it says if a line parallel to one side of a triangle intersects the other two sides, then I'm saying part of my given is that it's parallel. Okay, so one, I'm going to label my triangle ABC, and so I'm going to say triangle ABC, and we're also going to need to label that, and we're going to say DE is parallel to BC, and so that's given, that's part of what is the part of the given in the theorem. Okay, now what we're going to do is we're going to think about trying to use the parallel of the lines. So what are we trying to prove exactly? That's what we need to be clear on. And so if you think about what the proportionality theorem says, it says the line divides these two sides proportionally. So what I'm trying to show is that dB to dA is going to be the same ratio as CE to EA. And so that's what I'm trying to show. So think about similar triangles. If I was able to show that this little triangle there is similar to this triangle there, then that would mean that my sides are proportional because that's what a similar triangle does. So let's try to show that these two triangles are similar. So the next thing I'm going to do is I'm going to say, okay, because my two lines are parallel, I could say that this angle is congruent to that angle because of corresponding angles. So I'm going to say angle AED is congruent to angle ACB, and that's because of corresponding angles. Along those same lines, so just doing the same exact thing, on the other side I could say that this angle is congruent to this angle, same reason. So I'm going to go ahead and put that in there as well. So angle ADE is congruent to angle ABC, and that's under the same reason. So if you stop and look at what we've done, what we have now is we have two triangles that their angles match, and so that's going to be angle-angle similarity. So I can say that triangle ADE is congruent, or sorry, not congruent, similar to triangle ABC, and that is because of what's called angle-angle similarity. So if two angles are the same, then the third angle will also have to be the same, and any two triangles whose angles match up are going to be similar. We don't know that they're congruent because we don't know that the sides are the same, so we can say that they're similar. Now, if you have two triangles that are similar to each other, then their sides are proportional as well. So if I think about my little triangle, I could say side AE compared to the other side AD, and then in my big triangle AC compared to AB. So the reason that I'm saying that is because I'm comparing two corresponding sides of similar triangles. So the corresponding sides of similar triangles are proportional. If you think about the dilations that we've done on previous assignment and how the two shapes are similar and they have a scale factor, and so that's going to be the same idea here. Okay, so because of that, look at what we were trying to do. We were trying to say that dB to dA is equal to EC to EA. Now that's slightly different than what we have here, because what we have is we have AE compared to the whole side, AD compared to the whole side. But what we're talking about right here is we're talking about the sides of the triangles, but the same thing would be true for the pieces. So this piece compared to this piece. So it's going to follow that dB to dA is equal to CE to EA, and that's because the sides are proportional, and so their pieces are going to be proportional as well. Okay, let's go back down further in your notes. The next theorem is the angle bisector theorem, and so we're going to do the same thing where we're going to experiment and work with the theorem a little bit before we try to prove it. So the theorem says an angle bisector of an angle of a triangle divides the opposite side in two segments that are proportional to the other two sides of the triangle. So let's stop and think about what it's saying. If we have a triangle, if we have an angle bisector, so we have this given that it's a bisector, it says that it's dividing the opposite side into two segments that are proportional to the other two sides of the triangle, so our other two sides. So the theorem says that if this is an angle bisector, then, let me label this real quick. So if I have AE to EC, that's going to be the same proportion as AB to BC. That's what the theorem is saying. So let's go ahead and work with that first, and then we'll come back and prove this. So example number 4, you'll note that it's given that we have an angle bisector. And so this is splitting the opposite side, that's this side. So we're going to split it 4 to 10, and then it's going to be proportional to the corresponding side. So you'd have to do the x plus 2 first because that's the part of this triangle. So I'm going to say equals x plus 2 over 15. And so then I use my cross products to solve. So I'm going to have 60 is equal to 10x plus 20 when I multiply everything. Subtract 20 from both sides. And so x is equal to 4. So that means that this side is 6. And so if you look at our ratio, 4 to 6 equals 10 to 15. They both reduce to 2/3, so that's correct. Okay, let's go to the next one. Look for your angle bisector. So this is the angle, so that means that this side is being split proportionally. Now notice that 9 is the entire piece, and so we don't want that side. So we're going to have 3, and so the rest of it is going to be 6 because 6 plus 3 is 9. So now set it up. We're going to say 3 to 6 equals x minus 2 to 8. That's one way you could do it. You could also say 3 to x minus 2 equals 6 to 8. That's another way you could do it. As long as you're being consistent with what you're writing in your proportion, you can do a couple different things. Now, I like to have the x's on top when I solve a proportion. So I'm going to say x minus 2 over 3. That's this side to 3 equals, since I did that, I'm going to have to say 8 to 6. So then using my cross products, I'm going to have 6 times x minus 2 equals 3 times 8. I'm going to add 12 to both sides, and so x is equal to 6. So that means that this side right here, 6 minus 2, this is 4. So 3 to 4 equals 6 to 8. That's true. Okay, example 6, find the lengths of CD and BD. So CD is this one, and BD is this one. So I'm going to have to find x, and then I'm going to have to find those two lengths. So pause the video and see if you can figure out how to do this one, and then come back and see if you did it right. I'm going to set up my proportion x plus 2 over 7.7 equals x plus 1 over 5.5. Now, if you didn't set up your proportion exactly like that, just check your cross products and make sure that your cross products are the same. So as long as you did 5.5 times x plus 2 equals 7.7 times x plus 1, you're fine. Whatever you set up for your proportion is fine. So 5.5x plus 11 equals 7.7x plus 7.7. I'm going to get all of my x's on one side. So I'm going to subtract my 5.5x. I'm going to have 11 equals 2.2x plus 7.7. I'm going to subtract 7.7. So 11 minus 7.7 is 3.3 equals 2.2x. And so I'm going to divide both sides by 2.2x. And so I'm going to get 1.5. So now that I know that x is equal to 1.5, I'm going to put it back in here for x. So 1.5 plus 2 is 3.5. And 1.5 plus 1 is 2.5. So I'm going to check 3.5 to 7.7 should be equal to 2.5 to 5.5 if I did this right. So I'm going to use my calculator for this. So I'm going to type in 3.5 divided by 7.7, and I get 0.45 repeating. And if I do the same thing, 2.5 divided by 5.5, I get 0.45 repeating. And so that's true. So I know that my answer is right. Okay, let's go back to the theorem now, and let's look at how we are going to prove this. This one's kind of a harder theorem to prove, and we're going to need some auxiliary lines and so on. So let's start out with a picture, and so I'm going to draw this picture, and I want you to draw the same picture, and that's just because I've got the proof planned out. So here's my triangle, and I'm going to call it A, B, and C. And so I'm going to have an angle bisector, and so I could have any of the angles be bisected. But in order to do this proof, I'm going to have my angle bisector start at A and come over here. So we're going to start with AF is the bisector of angle BAC. and that's given. Okay, because the theorem says that we have to have an angle bisector, so that's part of the given part. Okay, now this is where the hard part of this proof comes in, because you have to stop and think about all these different possibilities, and I don't necessarily expect that you'd come up with this on your own, but let's see what we can do. We're going to actually use the triangle proportionality theorem that we just did to do something like this. So first thing we're going to do is we're going to extend this line. We're going to call that E. And then we're going to connect EC, and so you want to make E long enough so that EC will be parallel to AF. Okay, so we're going to construct this parallel situation. So I'm going to write number 2. Oh, hold on. There was something else to add to number 1. Let's go back in there. I'm also going to say that angle BAF is congruent to angle FAC. Actually, that is number 2. And that's the definition of what an angle bisector is. Okay, now let's go to our auxiliary line. So I'm going to say number 3, I'm going to extend AB to intersect EC, where EC is parallel to AF. And so all of that's because of a construction that I'm doing, an auxiliary line. So I'm just going to say construction because we're constructing it that way. Now, we're not actually constructing it with a compass and everything, but we're creating the situation that that's how we're going to make this happen. Okay, the next thing that we're going to do is look at your picture and look at angle ECA. So ECA is this one, and that is going to be congruent to this angle. Now, you might wonder, okay, well, why? So I'm going to draw something, then I'll take it off, but if I have this, and this is my parallel lines, and this is my transversal, then those two orange angles are alternate interior angles. And so I'm going to use that. So number 4, I'm going to say that angle ECA is congruent to angle FAC, and that's because of alternate interior angles. Now the next one that we're going to do is look at angle E, so that's this one down here, and that's congruent to angle BAF, this one. And the reason for that, again, think about your lines that you have. You've got this line as your transversal for these two parallel lines. So those two parallel lines, and so these greens are corresponding. So just so we don't have too much going on here, I'm going to erase that. But so we're going to say number 5, angle E is congruent to angle BAF, and that's because of corresponding angles. So if you think about what we've done, we started out by saying that these two red angles right here were congruent because of an angle bisector. Then we matched the two orange angles and we matched the two green angles. And so we can use substitution then to say that angle E, is congruent to angle ACE. So that's angle E, this one down here, and angle ACE, that's the orange one, and that's because of substitution. Okay, the green is congruent to the red is congruent to the orange, so the orange is congruent to the green. So substitution, it could actually be transitive property as well. Okay, now if you look at that, you're not really sure that we're getting anywhere. We are proving some angles are congruent, but how does that help us? Because we're still trying to get to proportional pieces. Okay, so the next thing we are going to say is that triangle EAC is isosceles. So write that down and then go back and look at your picture. Why is that isosceles? Why is angle EAC isosceles? It's because the base angles are congruent. So we know that if we have this triangle, if these two angles are the same, then it has to be isosceles. And so because that's isosceles, it means that this piece is going to be equal to this piece. Okay, so I'm going to take those extra colorings off there, but let's use that. So the next thing I'm going to say is I'm going to say that AC is congruent to EA, and that's because definition of isosceles. Now, if I've got these different pieces that are congruent, so I'm going to mark those. So I've got congruent pieces. And if we think about our proportionality theorem and the different things that it just said, okay, we know from our previous work, and actually we're going to be thinking about this big triangle as we're putting our next statement together. Think of that triangle, this line is parallel to this line, and think of the theorem we already proved. So because of that, I'm going to say that BA to AE equals BF to FC. And that's the triangle proportionality theorem, the one we just proved before. So you can pause this and look at that picture and see what we're doing there. Okay, and then the last thing that we're going to do, we're trying to prove what we were trying to prove in the first place. So what we were trying to prove in the first place is we were trying to say that if BF to FC, that's going to be equal to BA to CA. That's what we're trying to prove. So what we can say, since we have these two, or the proportions already set up, I can actually say then that BA to AC, okay, now stop and think, why can I say AC? Because instead of AE, I'm going to say AC because I already said that they're congruent to each other. So I'm just substituting something in, and then I leave the rest of my situation the same. Whoops. And that's what I'm trying to do. That's what I was trying to prove in the first place, so that's just substitution. Now, to understand this theorem and this proof, you are definitely going to have to go back through that and think about the pieces side by side and work through all the different parts of that. But that's how you would prove that theorem. Okay, so just to review, what do we know about similar triangles? If two triangles are similar, then their corresponding sides are proportional and corresponding angles are congruent. There are three different ways we can prove that two triangles are similar, and that's angle-angle similarity. So if they have two angles are congruent. We can do side-side-side similarity, and that's not that the sides are equal like it is with congruence, but the sides are proportional. So if your sides are proportional, then they would be similar. Or you could do side-angle-side similarity. That means that the two sides are proportional and the angle is congruent. So in the next problems, we'll look at how to work with those. Okay, you'll now need to go to the second video for the lesson.